There are times that we're interested in knowing if mean of one population differs from the mean of another population in certain direction. That would be mu of population 1 is greater than or equal to mu of population 2 or the other way around. In cases like this, we will be conducting one-tail tests. And the two possibilities are what you see here. Consider this very common scenario for fast food chains. Every time they decide to add a new menu item, much work and analysis goes into that decision. Every new item added must first show a significant demand before it is added. Every new item added increases the complexity of procurement of raw material, as well as requiring workflow redesign that goes along with it. The new item is added to menu of several outlets first, and then it is benchmarked against the demand for another regular item on the menu before a decision is made about the new item. So let's see how we will conduct and analyze such study. First, we like this new product to do better than another item. So that would be our alternate hypothesis, which can be written as mu of new minus mu of regular is greater than 0. So the complement will be the null hypothesis. Alpha here is 0.01. Once again, data collection is really important. We are going to collect sample data from two populations that are independent. One population has the new item in their menu, and the other population does not. Once we have the data collected, we will conduct our analysis to find the p-value for the difference we observe based on our data. The results from our data is shown here. The mean numbers are in thousands. Also note that we have different sample sizes. For the new item, we have 75 weekly sales data, and for regular item, we have 108 weekly sales data. Again, we are collecting data independently from each population. The sample sizes need not be the same. Since we are doing a one-tail test, the p-value we use to compare to alpha is this, and this value of 0.0045 is less than alpha of 0.01. So we will reject the null hypothesis. Rejecting the null hypothesis in favor of the alternate hypothesis implies that we believe the new item is doing better than the regular item it was benchmarked against. Thus, the management should consider adding this new item. Management is happy to hear this, but they want to know what is the expected difference between these two items before going nationwide with the new item. Given our results and the equation for the confidence interval of the differences between the two populations, we can find our answer. When you have conducted a one-tail test, now you're looking to find the confidence interval for the mean differences, where you could be wrong in both estimating the lower and the upper boundaries of the interval, then using the t-value of one tail, in this case 0.01, translates to having 1% chance of getting it wrong in either tail. Thus, the confidence interval in this case will be 98% confidence interval. I am showing you here how to calculate this difference piece by piece. First is the difference between the two sample means. Then we need the margin of error, which is T of alpha over 2 for a one-tail test in our case of 2.35 times the standard error, which means the margin of error turns out to be 1.168. So now we are ready to express the 98% confidence interval. Alpha here is 0.01. We find the 98% confidence interval to be 0.1517 to 2.488. And since the weekly sales were recorded in thousands, then we rewrite this as 151.7 to 2,488.22. In another word, we can be 98% confident the difference between average weekly demand for the new item is at the minimum 151.7 units more than the regular item. Look at how wide the width of this interval is. You may not like the width of this interval. This is in part because of the desired level of confidence we asked for. Remember that the larger the level of confidence, the wider this interval will be. But by and large, we expect this new item to sell better than the regular item we checked against. So now let's practice. A training program promises to increase the sales performance for most employees. The manager of sales department sends 80 of his employees to be trained through this program. If the results are shown to be better at 5% level of significance than a control group selected at random, then everyone will be put through the program. State the null and alternate hypothesis for this problem. Let's set mu1 to represent the average weekly sales for the control group, and mu2 represent the weekly sales for those employees who got the training. Since the training program promises to increase the sales performance for most employees, then we want our data to show that mu1 will be less than mu2. So that is our alternate hypothesis, and the complement will be the null. Now the data has been analyzed and is presented here. What is your conclusion at 5% level of significance? This is a one-tail test. At 5% level of significance, p-value for seeing a result like this is very small, which will lead us to reject the null hypothesis in favor of the alternate. It does appear that the training has helped the sales agent to become more effective. Managers should consider the training program for everyone. Now let's extend on this. The training program costs a lot of money. Before deciding to commit to this program, the manager wants to know the difference in weekly sales one can expect from this training. Now recall that for confidence interval, the 5% will be in both tails. Thus, our confidence interval we calculate here would be a 90% confidence interval. So now develop the 90% confidence interval for the difference. Use this output for calculating the 90% confidence interval. Again, for the confidence interval, the 5% will be in both tails. Thus, the confidence interval we calculate here is 90%. Using the output for calculating the 90% confidence interval, first, here's the difference between these two samples. Here's the t of alpha over 2. And here is the standard error. And now we can calculate the margin of error to be 65.83, which makes the 90% confidence interval to be negative 310.83 to negative 179.17. So what exactly does this mean? Recall that this is the average differences between the first group, our control group, and the trained group. The control group on average had lower sales than the trained group. That's why we are considering doing the training. But the management wanted to have a sense of what the difference can be before committing any resources to this. In this case, the control group average sales is less than the trained group. And the true value with a 90% level of confidence is somewhere between $179.17 to $310.83. What if the manager thinks that while this is good, it is not good enough to justify the cost? Could we test the hypothesis where we look for a certain level of difference rather than doing it this way? The answer to that is yes. And that is what we will learn how to do in the next lesson.